when we have two substituents on the aromatic ring, we have to do a little bit deeper of an analysis to figure out the product of an electrophilic aromatic substitution reaction. So what you're going to have to do is compare the substituents on the ring, and in this case we're doing two, but it could even apply to more substituents. And what you're going to find is that the stronger activating group directs the reaction. So that's what you want to look for. In this first example, we have a methyl group and a nitro group on the ring. The methyl group is an activating group. The nitro group is a deactivating group. So in this particular case, the nitro group directs meta to itself. The methyl group directs ortho-para to itself. The para position to the methyl is blocked by the nitro. So in this case, both groups actually reinforce the same position, so there's not a whole lot of analysis to make here. But perhaps an easier way to have just done this problem would be to look at your stronger activating group, which is the methyl group, and just see where it directs to. It's going to direct the reaction, and it directs ortho to itself. So in this case, we'll draw our product. Let's put the methyl in, the nitro, and then this was a chlorination, so we'll put a chlorine ortho to the methyl group. The next reaction is a sulfonation. Remember that the sulfonation is going to add SO3H to the aromatic ring, so that's your active electrophile. And with this, now we have groups that oppose one another. So the methyl group is an ortho-para director and an activator that directs to its ortho positions. The OH group is an ortho-para director and an activator that directs to its ortho positions, which are different than the methyl's orthos. These two groups oppose where they're directing to, so all you need to do is pick the stronger activating group. And from there, the OH directs ortho-para. So it directs its ortho positions. It also directs para, but that position is blocked by the methyl. So when we draw the product, here's our methyl, OH, and then we'll put the SO3H ortho to the OH group. The next thing that's really important to know about these disubstituted benzene rings is that the position between two meta-substituents is sterically hindered. So in this first case here, we have two methyl groups, and those two are meta to one another. And although they may not look that big, they take up enough space such that this position in between them is hindered, and we typically will not get electrophilic addition there. So then in this generic example here, the methyl group on top is an ortho-para director, so it can direct to this ortho position and to its para position. And then the methyl group on the right, it's going to be an ortho-para director, which can direct to this ortho position and this para position. So those essentially reinforce one another. So we would expect to get a product where the electrophile is here, and here. Now in this particular case, these two products end up being equal, of the same thing. Let's move down to this next example where we're doing a nitration. So in the nitration, we're adding an NO2 to the ring. And with this, what we can first look at is the fact that the methoxy group and the nitro that are on the ring are meta to one another. So just go ahead and put an X here between them to block out that position. Now between these two groups, the nitro group is a deactivating group. The methoxy group is an activating group. The methoxy group is going to direct the reaction. It's a more powerful activator. And it is an orthopara director. So it's going to direct ortho to itself and para to itself. So now we can draw the products for this reaction. We'll have a product where the new nitro group is ortho to the methoxy, and then a second product and in that one the new nitro group will be para to the methoxy.